effect in electronic crystals, but people are using this effect in photonic crystals. So you have a photonic crystal that is impenetrable, but if you add some impurity to it, the photonic crystal can allow you to send light through. Okay. So what else can we do with the photonic crystal? That's about all I can think of. But let me see how much time I have left. And with the time I have left, I'd like to talk about density of states and Green's function, if I could. So let's talk about density of states. Well, homogeneous medium is very simple. And we know that for a homogeneous medium, the solutions are just that, e to the ik dot r. For the periodic structure is more complicated than this, but let's talk about the simplest case. And then k can be any arbitrary vector. It will be the solution of the homogeneous vector wave equation. But unfortunately, k can be anything, so it's uncountably infinite. So we want to make this problem countably infinite. So we want to make k, instead of being a continuum, but making it into a discrete vector so that you can count it. So in 1D, this would be this problem over here. Kx is a continuum, but you want to make kx countable. So what we do is to set this up as a periodic boundary condition problem. Okay, you demand that this repeats itself. This function is 1 over here, but at the distance a, it repeats itself. So you have to have kx must be 2n pi over a. Okay, kx must be, this is called the periodic boundary condition. I can do the same thing to this wave, which is uncountably infinite. I can change it into a countably infinite thing, so that my k vector becomes x l 2l pi over a plus y 2m pi over b plus c 2e pi over d, by imposing periodic boundary conditions in 3 directions. Instead of solving this in an infinite medium, I solve it in the box. The box is confined to be a in the x direction, y in the b direction, in b in the y direction, and then b in the z direction. If you solve this as a periodic boundary condition problem, all my k vectors becomes countably infinite. I can count them. There will be infinitely many k vectors, but I can count them. Okay, this is what physicists are very clever for. They come up with these schemes so that you can count things instead of having to deal with continuums. So with this kind of thing, I ask myself, if I have a box, how many solutions can I have? I can call each of these solutions a state. Okay, I can call this solution as a state. How many states do I have if I were to solve for all possible solutions in this box? Okay, those are called a state. The density of states is a concept of if I have a certain frequency interval, or if I have a certain energy interval, how many solutions can I find? This question is hard to ask if these are not countable. But if these are countable, then it's quite an easy question to ask and answer. Okay. So, for instance, in 2 dimensions, if I were to draw this picture, kx, ky, I will find solutions that are at the periodic lattice points in the Fourier space. Those are actually the lattice vectors for this very simple structure. Okay, I will find solutions there. You know what these points are. I just want to draw them because they tend to laborious to draw their periodic points. And then the spacings will be 2 pi over a in the x direction. The spacings will be 2 pi over b in the y direction. Okay. In 3D, you have to add in one more axis, and then it will be 2 pi over d in the z direction. And there will be all these dots, and each of these dots represents a possible solution or possible state. And then it's easy to count the states, right? So if I look for the solution of this thing, like curl cross E minus omega squared over CE is equal to 0, then if this represents my omega C, then solutions exist when omega squared over C squared is equal to K squared. Well, omega squared represents the frequency, and in this case the energy, because in physics, E is just h bar omega. Okay? So I ask myself, if I have a certain energy value that I'm interested in, how many solutions are there? Like I might be interested in, if I keep omega constant, this is just the equation of a circle. In this equation, kx squared plus ky squared is equal to omega squared over c squared. If I change my energy of the system, the circle will just become larger and smaller. Then I ask myself, if I want to be looking for the solution in this interval, how many solutions are there? I can count this very easily because each of these solution occupies a volume that is something like this. Delta y is 2 pi over b. So each of them occupies an area of 4 pi squared over ab in 2D. Okay? And then in 3D, each of them would occupy a small volume of 8 pi cubed over a times b times d. This is 8 pi over b. Okay? So each of these states will occupy such a volume, and you can count how many states there are by dividing this shell either by this area, or in 3D you would divide the shell by this thing to count how many states there are. Okay, those are the ways of counting states in the Fourier space. And I just write down the solution for 3D. Okay, the solution for 3D is that the number of states that you have is 2 times 4 pi a squared delta k. This is the equation of a spherical shell divided by pi cubed over v. Okay, so that is the number of states in the shell. Okay, and physicists have a really clever way of writing down the equation for the density of states. The equation for the density of states can be just written as delta E minus epsilon k n. Okay. And actually, I don't have to bother you with n first, but this is like h bar omega. And this is like the all the solutions that you have found for different case. For different case, for different direction, you can always find a solution for this problem. Okay, I can convert this k squared to energy by just a simple multiplication, just like I can convert omega squared. I can convert k to energy. Okay, I can convert k to energy. I call this energy epsilon of k. So for every solution that I find, there will be a corresponding energy value. Okay. Okay, for every solution that I found for solving this problem, there will be a corresponding energy value. And I can write my density of states in this manner. A very clever way to write the density of states, provided that this is countable. This is countable because I use periodic boundary condition and can count them. Okay, these are all my E sub k solutions that I have. Okay, and if I write the density of states that way, I can easily find the number of states between a certain energy level. So if I want the solution between, say, this energy level, E plus delta E, I just take this function and integrate between the certain energy level. And using the shifting property of delta function, I will pick up all these energy states with that energy level. Okay, this gives you the number of states in that interval, and this is called the density of states. Okay. And this density of states concept can be extended to a photonic crystal. For the photonic crystal case, this diagram will not be a circle. Your omega versus k will not be that simple. That is, for different k vectors, you might have a surface that looks like this. Because when you solve this problem, you fix your k, you find your omega may not be the same in all directions, different directions of your locate wave. So your diagram might look something like that in the Fourier space. And then you can still write this function as the density of states. It's just that this diagram would be a little bit more complicated. This would be a rather complicated function of k. It will not be a constant. Depending on where k is pointing, you get different values. But you can still use this to write down the density of states. Are there any questions before we stop here? These are some of the concepts from solid state physics. It's good that we are learning photonic crystals now because the area of photonic crystals draws a lot of knowledge from solid state physics, density of states, local density of states, and then how to count things and so on. And this is a good chance for you to learn something about solid state physics, which is used in understanding the nature of solids. Okay, any questions? Okay, we'll talk more about it next time.